In this lesson, we are going to look at how energy is related to heat and enthalpy. So, first of all, we know that energy is often measured in joule. Okay? So let's look at heat and enthalpy. First of all, enthalpy, basically all substance has a certain enthalpy. What is it? It's basically the sum of the system internal energy. So every substance or every matter has some sort of internal enthalpy. That's because they have certain amount of energy in it. Now, of course, energy is measured in joule, represented by the letter J. Now, what about heat? Well, heat represented by Q, where enthalpy represented by H, which makes sense, okay? Think of enthalpy as like the heat content of a system. Now, where heat is the energy being transferred, so this energy is moving from one place to another place. So when a substance is gaining energy, that energy that being transferred in is considered as, and when a substance is giving up energy, that energy is also known as heat. So again, heat is the energy that transfers from one object to another object at constant pressure. That happens to be an open environment. There is no control of the pressure. So one thing we need to keep in mind that energy naturally will always flow. I mean, it will always go from one place to another place. Specifically, it will always flow from a system of higher temperature to a system of warmer temperature. Basically saying that if you have a hot object in contact with another cold object, that energy in the hot object will go to the cold object. Eventually, both systems have the same temperature. Okay? So it's always flow from high temperature to lower temperature. Now, notice how we say enthalpy is the sum of internal energy. But what happened if the internal energy change? We have delta H. We call it change in enthalpy, okay? So in a way, isn't this the energy being transferred, either releasing or gained? And that's the reason why we have delta, which is delta, this is the symbol for delta right here, and delta is usually represent change. So the change in enthalpy of a system equal to heat. That is the energy being transferred from one place to another place. Now Q, which is heat, is equal to this equation. Q is equal to mass times specific heat times delta T. And again, delta T is the change, right? When we look at change, what are we really looking at? The change is always relative in terms of final. In this case, so we have delta T, that's T final minus T initial. So every time you see delta T, always think of final minus initial. And of course, I further describe them here. Q again is the quantity of heat, the energy being transferred, and is measured in joules or calories. Well, M is mass in grams. And of course, delta T is T final minus T initial. And lastly, this is where the most important piece of all is the specific heat capacity. Why is it important? That is because it tells you what unit M need to be. Notice how we have G, that tells you gram. Notice how J, that tells you your Q must be in joule. And look at the C. So what is heat capacity and how is it different from specific heat capacity? Well, first of all, heat capacity is the energy required to raise 1 degree of Celsius, okay? So how much energy, that's why we have joule over Celsius. How much energy do I need to raise 1 degree Celsius? Whereas specific, think of the term specific, that's because different substances have different heat capacity. Well, if we look at the unit of specific heat capacity, we have energy, right? And how it's being divided by gram and Celsius. Basically saying that different object has different heat capacity. That's because it's required different amount of energy to raise 1 degree of Celsius for that 1 gram. So keep that in mind, is per 1 gram of the substance. That's very important, okay? So that's specific heat capacity. Now, if we look at the list of specific heat capacity, what does it tell you? Of course, the one with the lower J right here is the one with the lower J right here. Okay? So that would require very little energy to change the temperature. So keep that in mind. And where the one that has very high specific heat capacity, it would require a lot of energy. For instance, metals have very low specific heat capacity. That's why we use metals in our cookwares, so that way it easily increases the temperature. Isn't that nice? So we can cook faster. You already know that the amount of energy in this universe is constant. What does that mean? That energy is neither create nor destroy, just like matter neither create nor destroy. Okay, so if that's the case, the amount of energy is being lost should be equal to the amount of energy being gained. That's why we have negative Q equal to positive Q. So that's the concept behind it. And one of the most common equipment that we use to determine how much energy is being released is a coffee cup. Think of the word coffee, okay? We use a coffee cup. And a coffee cup, if you ever hold a coffee cup before, it is very well insulated. So that means all the heat that's being released by the system in this container, it will be changing the temperature. So we can measure the change in T, and once we get the change in T, we can actually solve for specific variable in the equation. So we're going to look at those more specifically. So again, know that we are using a coffee cup calorimeter. Okay, calorimeter. Say that again. Calorimeter. Now let's try one problem together. How about that? How many joules are needed to warm 45 grams of water from 30 degrees Celsius to 75 degrees Celsius? The specific heat of water is 4.184 joule per gram Celsius. Okay, so if we read this problem, we know that we are looking for joules, so that'll be Q. Easy, isn't it? And we know that that would be your mass because it's a gram right there, and of course is in the right unit as well. And then we are going from T, this is your TI, which is your initial, and we're going to TF. So we do that, we can just solve. Now let's use the equation. We know that Q equal to MC delta T. And the one way you can remember this is MCAT. Think of the delta, look like letter A, isn't it? So we call this MCAT. Q equal to MCAT. Okay? So in this case, your mass is 45.0. And notice how I don't put the unit there. Okay? And my specific heat capacity is 4.184. Again, I did not put the unit there. That way it doesn't confuse us. And then the last thing we have is delta T, which is T final minus T initial. In this case, it is, we know exactly what it is already. The T final is 75.0, and the T initial is 30.0. And then all we have to do is just plug this into the calculator. Isn't that easy? So if you plug this into your calculator, what you have is 8470. And we want to keep 3 sig fig because our answer. So what is the unit for Q again? Of course, it's joule. And there you go, that is your answer. Now in this case, what happened to the system? Is it gaining or losing energy? Well, if you look at this water, it's starting from very cold temperature of 30 degrees and get really hot to 75. So the only way that's possible is gaining energy. Okay, let's try another problem. A sample of lead, its specific heat capacity, my bad, okay, is 0.138 joule per gram in Celsius. Release 1200 or 1200 joules when it's cooled from 93 degrees Celsius to 30 degrees Celsius. What is the mass of this sample of lead? So again, Q equal to MCAT. Okay, and we know a Q in this case is down right there, which is 1200. Then do we know our M? Our M in this case is what? We don't know. We are looking for the mass, so M right there. And we know the specific heat is right there, so which is 0.138. And do we know our delta T? Of course, from final minus initial. In this case, the final is 30. and 93. Okay? Isn't that easy? And of course we know that this is losing. Notice how this system is losing energy. And how do we know? It's starting from a very high temperature to a very low temperature. So this key over here, there's one last tricky part. So that when it loses energy, it's actually a negative. So we have a negative 1200 joules. So how is that going to affect our answer? Of course, if we do the math behind it, look at this number. We take 30 minus 93, that gives us 63, specifically negative 63, isn't it? So if we plug this into a calculator, of course, we have negative 63 times 0.138. And notice how we have a negative answer, okay? So notice how when we plug this in, notice how when we calculate it, we have a negative answer. So we have m times negative 8.69. Okay, let's keep 3 decimal places for now. And that's equal to negative 1200. And what is m going to be? Of course, we're going to divide both of this side by negative 0.694. Answer. So your m is going to be 138.03. And for this case, we're not going to care about sig fig that much. Just skip that right now. I just like to keep this 2 decimal places. So what's the unit for mass going to be? Of course, it's going to be grams. And specifically what chemical? Of course, it can be lead, Pb. So your mass is equal to 138.03 grams of Pb. Let's try another problem. What would be the final temperature if 3,310 joules were added to 18.5 grams of water at 22 degrees Celsius? Well, again, going back, this is your Q, this is your M, and this is your what? Well, of course, this is your Ti. And what about Tf? We are looking for Tf right there, isn't it? So again, Q equal to M cat. Well, M in this case is 18.5. And what is our C going to be? We know that C for water is 4.184, which I recommend you remember. And our delta T is Tf minus, which we don't know. Ti in this case is 22. So can we simplify this? Of course, it's so easy. Well, before that, let's plug in the joule, which is 3310. Well, in this case, do we know if the Q is positive or negative? Well, look at the question. We have 3,310 joules were added. So that means it has to be positive. Okay? So let's simplify this. I'm going to multiply this and get a number. And of course, in this case, I have 77.404 times Tf minus 22. And over here, we have 3310. Can I divide this both sides by 77.40? 740. That cancels out, of course. And we have 42.76 equal to Tf minus 22. Well, this is easy. You just need to bring this over here, right? So your Tf is going to equal to what? Well, 42.76 add 22 and give us 64.76 degrees Celsius, and that would be your T final. So if you add that much energy in, the water will increase from 22 degrees Celsius to 64.76 degrees Celsius. Now, are you ready to try some of the AP Chem question? Well, in this case, we have a 300 gram sample of mercury with specific heat capacity, or sometimes we just say specific heat, equal to 0.14 joule over grams in Celsius. And the initial temperature is 22.00 Celsius. It's placed in 130 grams of water. The initial temperature is 35 degrees Celsius. Well, what's missing about water? Every time you see water in this type of problem, you need to know that water has a specific heat capacity, okay, or CS or CP sometimes, which is 4.184 joules over gram of Celsius. Okay, so keep that in mind all the time when you see water. What is the final temperature of the system? This is supposed to be system. Okay, now notice how this becomes more confusing because you have two systems combined together. So remember, going back to the ideas of when we have Q equal to, or Q gain equal to Q loss, or Q loss equal to Q gain. And this is important because remember, when we're talking about the system of the calorimeter cup or the coffee cup calorimeter, when we have two systems, one system is going to be the water and the other system is going to be in the water, either absorbing the heat from the water or releasing the energy from the water. So that will cause the changes in the temperature. So again, that's the concept behind it, is using or understanding of how energy is conserved when two systems interact. Well, in this case, which one is gaining the energy? Well, look at water. Water is 35 degrees Celsius, where mercury is 22 degrees. Well, in this case, water is going to lose its energy. So we would have water as negative Q, where the mercury would be a positive Q because gaining the energy from the water to increase the temperature in a way that's no longer 22, it's going to be something else. But let's go back to Q. Q is equal to M. Again, Q is equal to M cat. Keep that in mind. And we know M in this case is 300. Okay. Do we know a C? Yes. 0.14. Okay. Notice I don't put the unit there. And do we know our delta T? We know T initial, but we don't know T final. So our T initial in this case is 22 degrees. Okay. And this is for the mercury, Hg. Now the other system that this mercury is going to put in is water. And we know the mass for water is 130 grams, okay? And do we know the specific heat for water? Yes, 4.184. And that's going to be tricky if it's not given to you. And your delta T, we don't know T final, but we know T initial. And if we look at this, notice how Tf is the only variable that's left in this equation. So all we have to do is simplify this equation to solve for Tf, which is a basic variable like x and y. So let's do this. We can multiply this, okay, and we get a number. And then, well, in this case, what would it be? We have 42 Tf minus 22. And over here we can simplify this. What we have is, of course, keep that in mind, it's negative. I totally forgot about that. That's negative Q here there. So it's negative 543.92 times Tf minus 35. Okay? Now we can distribute this in. Alright? The same thing in this case. We can distribute it in. And what do we get in the end? Of course we have 42 Tf minus, and 42 times 22, that gives us 924 right there. And over here we have, of course, 543.92 Tf, and this time 35 gives us a very large number, 037.2. There you go. Now notice how we have Tf and Tf, we can combine them together based on like term. We would bring this over here, okay? So we bring this over here, and I totally forgot about the negative. Oh, my bad. So this would be a negative, and this would be positive, because this negative here, this negative time a positive gives you a negative, where this negative time another negative will give you positive. I totally forgot about that, my fault. Okay, so now if I were to bring this over, of course, this is going to be add, right? So this is going to be add over here. What we're going to have is 585.92 Tf. And if we bring this over here, this side, we're going to add, right, because it's negative. So what we have is 96120. And how do we solve for Tf? We just divide both sides by 585.92, 585.92. And Tf, okay, let's do this. Tf is equal to 34.07 degrees Celsius. Whew, isn't that a long problem? And this is probably one of the hardest questions that you will see on your AP Chem if you are dealing with this type of problem. And again, the way it works is that if I would draw this calorimeter cup, I have water in here, and the water is going to be 130 grams. Then I would put my mercury in here. So this would be my mercury at 300 grams of Hg. And of course, the water's energy is going to absorb by the mercury. And what happened to the temperature of the water, which we can read with a thermometer easily, right? It changed over time. And that's the concept behind it. Isn't it easy? Now, let's try one of the last problems that you might see on the AP Chem. So, we have 84 gram sample of unknown solid metals at 600 degrees Celsius, and is placed in 75 grams of water at 30 degrees Celsius. And of course, if we read this, the water, it is 30 degrees Celsius, not the piece of metal. Okay, so this is your Ti of your unknown metal. This is your Ti of the water, and it tells you the final temperature of the system, which means for both the metal and the water is this. So this Tf for both. The question asking us is, what is the metal? And we are giving a list of specific metals and their specific heat capacity. So again, we are dealing with two systems. We realize that, of course, positive Q is equal to negative Q, assuming no heat is being lost to somewhere else. Well, in this case, what is going to be lost? Or if you want to think of this way, you can think of negative Q equal to positive Q. It doesn't really matter, okay? So, whatever, we're going to use this one. How about that? In this case, if our negative, which one is our negative Q, we have to realize that the metal is at 600 degrees Celsius and put in 30 degrees Celsius of water. Of course, that metal is going to lose the energy, okay? So we know the no metal is going to be the negative Q. So we have 84, that's your mass. Again, going back, Q is equal to MCAT, right there. So 84, and we have a specific metal? We don't. We are solving for it. That's the reason why we're looking for the piece of metal. And once we know the specific heat capacity, we can correlate them and determine the identity of the metals. So we know that we are looking for C of metal, CS specifically. Okay, and what about the delta T? Well, T final is 50 degree and T initial in this case 600 degree. There you go. And don't forget about the negative. That negative will cost you the whole entire problem. Then over here we have the positive, okay, which the mass of water is 75.0. That's easy. And then what about the specific heat of water? Remember, it's 4.184. And then the delta T is 50 minus what? Well, in this case, 50 minus 30. Final minus initial. And if we were to simplify this right here, we plug this into a calculator, we have 6276. And if we simplify this and that, and we multiply together, we would have CS time 46200. And can we divide both sides by 46200? Of course. 46200. And of course we get a really small number for CS, 0.136. And what's the unit for it? Of course, it's joule over gram Celsius. And look at the table, which one has the same or similar specific heat? And that's right there. So this must be your unknown. So the metal must be what? Tungsten. Isn't that easy? And that's all you have to do.